Okay, so welcome to this video on variance and the law of the unconscious statistician, Lotus. Okay, variance then firstly. So this is the setup that we have. So I'll just put the title, variance, and this is definable for continuous and discrete random variables. Okay, so this is the setup that we have. We have an abstract probability space over here, omega curly f with a probability measure, and then we have a random variable x, which is mapping it onto some probability space with outcomes in the real numbers. Now, one of the main the reason we did this, the reason we wanted our outcomes to be mapped onto real numbers, is firstly so that we have a nice way of handling our outcomes, you know. So instead of having to write each of the outcomes out, we can just label them with real numbers. But one of the main reasons we did it is because we want the algebraic properties of the real numbers to be able. We want our probability space to have those algebraic properties of the real numbers on it. So what we do is we find this map which preserves the probability space structure on here, but this has other structure as well, which is that it has the addition and multiplication properties of the real numbers. So on this we have additional structure apart from just the probability space structure that it inherited from here, and we saw the use of this algebraic structure in defining the expected value. Now the expected value gives us kind of an average value. It gives us sort of like the middle value, if you like. What if you did it enough times and then you took the actual average result, what would you overall get, is a way of viewing what we did there. Now what we want is a measure of how spread out the distribution here is, how spread out this probability distribution is. So for instance, if we look at some simple not simple, but if we look at some probability distributions like this, so let's say we'll go for discrete random variables at the moment, because discrete random variables we've done a lot more with than we've done with continuous random variables. So I don't suddenly want to start leaping in with continuous random variables just because I've made one video now on continuous random variables. So let's do some discrete random variables. So for instance, let's have the same, let's have 0, 1, 2, 3, 4, 5, 6, and 7. So let's say these are all the possibilities that you can take on. So this is our set over here. These are all possible outcomes of our experiment. So we've had our abstract probability space, and they are mapped onto all of these are the total number of possible outcomes. Okay, so we could have a probability distribution that looks like this. So I want to make sure they add up to the correct thing. So we could have, let's say those are both equal to, so this is the PMF I'm plotting here. So the probability that it's equal to 3, let's say, and 4 is equal to the same thing, and that's equal to a third. Then we could have, for instance, let's say this is, okay, no, that's not going to work. So we're going to have to go down quite a bit now. So all we've got left now, we want it to add up to 1, remember. So all we've got left is a third. So let's divide it equally among those things. A third divided by 6 is equal to 1/18. So the rest of them are going to have to be 1/18 likely. So something down here. So we'll give them all 1/18. Okay, so it's pretty clear that the expected value of that is, because it's so symmetric, it's just going to be 3.5 here. Okay, if you wanted to actually see that, we could add it all up. We could say 1/18 times 0 plus 1 plus 2. So we could have 0 plus 1 plus 2 plus 5 plus 6 plus 7. So I'm just following the formula for calculating the expected value, which is that you multiply you go over each possible value, you multiply it by the probability. So the probability of all of these ones here, 0, 1, 2, 3, 1, 2, 5, 6, 7, is all 1/18. So this is the bit for 1/18, and then we've got plus a third, and then the 2 in the middle, 3 plus 4. So if we add all of that up, then here we get 0 plus 1 plus 2, that gives us 3. Plus 5 is 8, plus 6 is 14, plus 7 is 21. So we get 21 over 18, plus here we get 7 over 3. So if we multiply, well, here we can cancel something. Did we get yes, 21. So here we can cancel because 21 is a multiple of 3 and 18 is a multiple of 3. So this goes down to 7 over 3. So we get plus, sorry, not 7 over 3. Divide the top by 3 and you get 7. Divide the bottom by 3 and you get 6, don't you? Yes. Plus 7 over 3. Right, so multiply this one by 2, multiply top and bottom by 2, and you get that's equal to 14 over 6. So now we can add them both together, and overall we get 21 over 6. And again, we can cancel that down by dividing top and bottom by 3, and we get that it's equal to 7 over 3, which is indeed equal to... Oh, sorry, no, 7 over 2, which is indeed equal to 3.5. Oh dear, 3.5. So there's the expected value of that probability distribution. Now, if we take another probability distribution, that's just going to be the uniform one. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8. Now we have 8 points, so let's just ascribe to each of them 1/8. And this probability distribution is just going to be 1/8. Well, the expected value for this probability distribution is just going to be 1/8, the probability of them all, times by the sum of them all, which is the sum from 0 all the way up to 8. Plus 4, plus 5, plus 6, plus 7, plus 8. Okay, so if we do that, 1 plus 2 is 3, plus 3 again is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21, plus 7 is 28, and plus 8 is 36. So 36 divided by 18, they both divide by 6 rather. So 36 divided by 6 is 6, 18 divided by 6 is 3, and you get that, oh dear, that doesn't look right. Where have we gone wrong here? I would have thought the expected value should have been 3.5, the right centre. That's giving us the answer of 2, though. Oh, sorry, I'm dividing it by 18 because of the previous one. Divided by 8, that's the problem. So 36 divided by 8, they both divide by 4, we get 9 over 2. Oh dear, it's gone wrong again. 36 divided by 8. What am I doing wrong here? Oh, I can see. There aren't 8 values here, are there? We've got 4. And that one only went up to 7 is the problem. I'm going completely gaga. Sorry. Cancel all of this. This is all wrong. The probability is 1/8 because you do have 8 values. 0, 1, 2, 3, 4, 5, 6, 7, 8. So you have 8 there because 0 is counted as 1. So the probability is an 8, but you only add up 0, 1, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7, and that's it. You stop there. Okay, and then if you do that, we did the sum over here, you got 28. 28 over 8. Both of those divide by 4, you get 7 over 2, which is indeed equal to 3.5. So both of these distributions have the same expected value, but they are very different distributions. This one is, this one here is far more spread out than this one up here, which is far more centralized. Okay, so variance is going to give us a way of measuring how spread out a distribution is. So, the way we're going to define variance, the variance of a random variable x is going to be the expected value of the random variable x minus e of x, and then this is the bit people don't understand. You square it, and it's the expected value of all of that. So what are we doing here? So if we take a random variable, remember what that is. It's this mapping from our abstract probability space P, and we are mapping it onto a standard we're mapping it onto the real probability space with outcomes in the real numbers. Okay, so each outcome here has some value in here, which is x of s. So what you are doing is for each outcome you are saying take away the expected value of x. So take away the expected value of x. So that will give you another real number. So basically what we can do is we can set up another mapping, which we'll call x bar, which is going to map every single point in here. It's going to map it onto x of s minus e of x. So e of x is just some fixed value. You can work it out, the expected value of x. It is some real number. So what you're doing is you're taking every number in here and you are mapping it onto that real number, take away e to the x. So if we take the composition of these two maps, you get another random variable. It's going to take every value in here, it's going to take every outcome in here, and it's going to firstly map it onto here, a real number, and then this mapping is going to map it onto another real number. So we can overall compose those together and get an overall random variable from here to here. Okay, now we can take this further. We can go another step and we can say let's square this, so square everything. So you map every real number on here onto its square. Now you see the problem with this is that this will measure the distance from every value, every real number, from the expected value, from the mean, if you like. The problem is that if you take the expected value of that, if you take the expected value of this random variable here, the expected value of y, you'll find that it's equal to 0. And the reason is that if we take the expected value of y, we know that y is equal to x minus e of x. So we know that it's equal to x minus e of x. Okay? So this is our random variable y. Now if we take the expected value of this is by linearity, it's equal to the expected value of x minus the expected value of the expected value of x. But the expected value of x is just a constant. So if you view that as a constant random variable, then its expected value is just its value. So we get e of x minus e of x. So the expected value of y is going to be e overall equal to 0. So remember linearity. Think of this as a random variable. Think of minus e of x as a random variable. So you could think of this over here, minus e of x, which is just going to map every single outcome onto e of x. If you take the expected value of that random variable, which we could call it z, then it's going to be equal to 0. And by linearity, the expected value of y is the expected value of that random variable minus the expected value of that random variable. So we overall get that it's equal to 0 rather. Okay, now we can square it, which will get rid of this problem, because basically what it will do is it will map every single one onto every single one of these, it will map onto a positive number now. So it gets around this problem that all the positives are cancelling the negatives out, basically. Well, all the negatives are cancelling the positives, basically. So what we get overall is that we have another random variable here, which we'll call, what can we call this? T, let's say. T, which is basically going to be take your s, map it onto whatever x maps it onto, then subtract off e of x, which is just some constant, and then square the value, and that's overall going to be what t maps s onto. So this is t of s, if you like. Okay, and then basically what we can say is what's the expected value of t, and that expected value of t is what we're going to define to be the variance of the distribution x. So it's equal to the expected value of x minus e of x squared. And now would be quite a good time for me to introduce some other notation for expected values. So often when people write e of x, they will just drop the brackets. They will just write this e of x. And here it's quite nice because here we've got brackets everywhere. So it would be quite nice just to write this e of x minus e of x and then square all of that, wouldn't it? So this says the expected value of the square of x minus the expected value of x, basically. But we have dropped quite a few brackets there. Okay, by getting rid of this need to put brackets around the random variable. Okay, so we can work out what this is. In principle, at least, you can work this out. For whatever random variable I give you, I can work out what this random variable t is. So if I had a finite distribution here being mapped onto a finite number over here, finite probability space here being mapped onto a finite probability space over here, I could actually go through and work it out for each single one and work out this this random variable for you. Well, work out this value for you, this variance of x. And again, you'll just get some real number. Okay, so what we can do is we can say that this is the expected value of, and now we can just expand this out, and we get x squared minus 2x e of x plus e of x squared. Now this is where we apply linearity. We say that this x squared is another mapping. This is another random variable. So if we go up here, we could just have square here. We could just square each of these values here, and we'd get another real number. And this composition of these two maps would just be x squared, that random variable there. So expected value of x squared minus 2ex is just a constant, so by the first property of linearity we can just pull that out, and then it's the expected value of this bit here left over, and then we get, this is just a constant, so the expected value of that is just the expected value of x squared. Now this cancels with this, and we get that it's equal to the expected value of x squared minus the expected value of x all squared. So if we put the brackets back now to make it really clear, it's the expected value of x squared minus the square of the expected value of x. So that's the difference between this term and this term. Okay, so that is a formula that you often see for calculating the variance of a random variable x. And in a way, what it's going to do is it's going to measure how far each of these points is away from the expected value of x. So basically, if we imagine doing it for this probability distribution here, what we do is we'd take each one of these. So what we do is we map each of these outcomes here. So in fact, let's do this. Let's get some more paper here. Keep that here. Okay, so what we do is we'd map each of those onto what they are, take away e to the x. So we're doing this bit here, basically, this mapping here, where we're taking each real number and we're subtracting off e to the x. So what we get is we'd get, 0 minus 3.5 is minus 3.5. Then we'd get 1 minus 3.5, which is minus 2.5. Then we get minus 1.5, minus 0.5, 0.5, 1.5, 2.5, and then 3.5. Now, the probability distribution on this would still be the same. So the PMF of getting minus 3.5 would still be 1/18th, 1/18th, 1/18th. Minus 0.5 would spring up to a third because that was the point corresponding to 3, and it will remain like that. So the probability distribution hasn't changed. All you're doing basically, is relabeling the points, relabeling the outcomes, and inheriting the same probability space structure. All you're doing, that's the best way of thinking about it, is all you're doing is relabeling the outcomes. You are saying, let's relabel each outcome with the outcome minus the expected value, basically. You are not changing the probability space structure. You are saying, keep all the events the same, keep all of the probability measure the same. It's just I'm going to change what the outcomes are called. Therefore, just update in your set of events. Just obviously update all the sets so that they contain the correct outcomes. But as far as the probability space structure is concerned, don't change it. So this is why we've still got the same probability space structure, just with different names for each of the outcomes. Okay. And now what you can see is that if I were to take the expected value of this, I would get 0 right in the center here. So what instead you do is you square each of these. Basically what you're going to do is 0.5 and negative 0.5 are going to square onto the same thing. So now what you're going to do is effectively like a homomorphism, a probability space homomorphism. You're going to map 0.5 squared, 1.5 squared, 2.5 squared, and 3.5 squared, and you're going to map this one onto this one. This one will also go onto this one here. This 2.5 and this negative 2.5 will go over here. Negative 1.5 will go here. 1.5 will go here. 0.5 will go here, and negative 0.5 will also go there. Okay, so that's how you're going to. That's the process of squaring it all, and you're going to get another probability space, probability distribution here, and what you're doing is you're taking the expected value of that new probability space distribution, and that will be somewhere over here, and that's what we're calling variance. So this mapping here is going to be a homomorphism with respect to the probability space structure. So this is going to inherit the probability space structure of this. So 0.5 squared is going to have probability 2/3, because it's the probability that you're either negative 0.5 or 0.5, and then each of these is going to have probability 2/18. 2/18. So if we actually work this out, let's actually work this out. So this is the probability distribution for this one here. And if we actually wanted to work out the variance, the way we do it is we take the expected value of this probability distribution now, which is the sum over every single possible value of x, times that value of x times the probability that this random variable, which we'll just call t for now, t, is equal to x. Okay, so we get is equal to 0.5 squared times 2/3, and then we're going to get plus 2/18 times 1.5 squared plus 2.5 squared plus 3.5 squared. Okay, so if I get my calculator and actually work that out for you, we will get a measure of the variance of this distribution. So, okay, here's the calculator. So 0.5 squared times 2 divided by 3 times 2 divided by 3. Okay, so that's going to give us 1/6 there. So this bit's going to give us 1/6. Now let's work out this bit over here. So if we add up 1.5 squared plus 2.5 squared plus 3.5 squared, and then we times that by 2 and divide it by 18, and then we add 1/6 to that, then we get that the expected value is approximately 2.47 approximately. So that is our variance. Okay, now to correct the fact that we squared it earlier, which can be awkward because you change the units of that you're working in, there is another concept called standard deviation. The standard deviation of the random variable x is then the square root of the variance of x. So in this case what we do is we do the square root of 2.47. So that's another very important concept. Okay, so now what we're going to do is we're going to tackle the problem of the question of a lotus, which is the law of the unconscious statistician. And basically, the law of the unconscious statistician, lotus, is this, that the expected value of some function g of x. So basically, for instance, g of x could be equal to x squared. This is the motivation for why we want this. Or it could be something like sine of x. So what do we have? Let's just recall what a random variable is once again. We have our abstract probability space. We have a random variable x, which is mapping you onto a standard probability space in the real numbers. We could then have another function, g, which maps you onto some other real numbers, and all we're going to consider this doing, we're going to consider it just relabeling each of these real numbers by another real number. Of course, it could be like x squared, where it's going to be mapping multiple real numbers onto the same real numbers. It might not necessarily be a complete relabeling. We might be relabeling some as the same thing, so they become the same thing in this under this new relabeling. But that's okay. So we have this function g, which is going to relabel our probability space, our standard probability space structure here, with other real numbers. And it could take any of these forms. And basically, if we consider this new random variable here, and we want the expected value, we'll call this new random variable g of x. If we want the expected value of g of x, then the law of the unconscious statistician says that this is equal to the sum over all possible values of x, g of x times the probability that x is equal to little x. So this is little x here. each value, so you basically take each little value of x in this bit here, you take g of that value, so you take what value is it being mapped onto, and you times it by the probability that x was equal to little x here. Now that's pretty intuitive, basically, because this is going to inherit the probability space structure from this one over here. So all you're doing basically is relabeling each of the elements. Each element in here is going to be relabeled by g of little x. So we want to, if we want the expected value of, g of big X, I want the expected value of this random variable here, then it's going to be the sum over all possible values. So let's say all possible values little g of that little value g times the probability that g of x is equal to little g. Now, all possible values of little g, if we let it sum over all possible values of x, i.e. all possible values in here, and then take g of little x, then we will get all possible values of g. Now, it's inheriting the probability space structure from here, so the probability that you get that little g of x is going to be equal to the probability that big X was equal to little x. So the law of the unconscious statistician is pretty intuitive. Now the same thing holds true in the continuous case, where the expectation value, as we've discussed, is a little bit different. The expectation value in the continuous case is equal to the integral between negative infinity and infinity of x times the probability density function f of x dx. Now the law of the unconscious statistician says that the expectation value of g of x, this function of the random variable, is going to be equal to the integral between negative infinity and infinity of g of x f of x dx. And the reason that this is so useful is that if we want to calculate e of x squared, meaning if I return the brackets e of x squared, I will always write, if I omit the brackets, I will write e of x squared, the other e of x squared, like that, meaning the expected value of x and then take that number and square it, rather than take the value squared and then find the expected value. If we want to find that, it means that it's going to be equal to the sum of x squared, the probability that x is equal to x, times x, over all x rather. Or if it's a continuous random variable, it's the integral between negative infinity and infinity of the probability density function f of x dx. So that's going to be very helpful when we actually